we are Group 4, and our members are Apita, Deudor, Flores, Gilo, and Paikana. We are here to present the SAP1 circuit together with our modified circuit, which is the shift left register. First, let's talk about SAP1 architecture. Generally speaking, simple as possible or subcomputers were created to expose newcomers to some of the fundamental concepts that underlie computer operations. Each step of subcomputing is more developed and takes advanced computer architecture principles into account than the one before it. The SAP1 computer represents the beginning of this progression and is equipped with the essential components for a usable computer. Its main goal is to provide readers a fundamental understanding of how computers operate, interact with memory, and cooperate with other components of the system like input and output. There is a relatively small number of straightforward instructions. The SAP1 computer uses one Newman architecture and is bus organized. It uses an 8-bit core bus and consists of 10 major components. And these 10 are namely program counter, input NMAR or memory address register, random access memory or RAM, instruction register, controller sequencer, accumulator, other subtractor, B register, output register, and binary display. Next.
So the program counter is a register that holds the address of the next instruction to be executed. It is typically incremented after each instruction is executed so that it points to the next instruction in memory. And then the memory address register or the MAR is the one who holds the address of the memory location to be accessed. In the case of the SAP1 shift left register, this is typically the memory location that contains the instruction to be executed. So next, the RAM is the main memory of the SAP1 shift left register. It is a collection of storage locations, each of which can hold a binary value 0 or 1 and is used to store both data and instructions. Instruction register is a register that holds the current instruction being executed. The instruction is fetched from the memory location pointed to by the program counter and loaded into the instruction register. The control unit is responsible for controlling the flow of data and instructions through the SAP1 shift left register. It reads the instruction from the instruction register and interprets it, sending control signals to other parts of the computer as needed.
We also have accumulator. It is a 8-bit buffer register that stores intermediate results during a computer run. And then the ALU, other subtractor. This module is asynchronous, which means that its contents can change as soon as the input words change. And then the B register, it is a 8-bit buffer register, which is primarily used to hold the other operand of mathematical operations. And then the output register, this registers holds the output of out instruction. And then the last is the binary display. It is a row 8 LEDs to show the content of output register. Binary display unit is the output device for the SAP1 microprocessor.
So first, a shift register is a group of flip-flops which is used to store multiple bits of data, and that data is moved from one flip-flop. It is a kind of digital circuit which performs two basic functions, which is data storing and data shifting. The bits stored in registers shifted when the clock pulse is applied within and inside or outside the registers. A shift register can shift the bits either to the left or to the right. A register which shifts input data towards left are called shift left registers. It is a digital circuit that shifts the bits in a register to the left by a certain number of positions. Let's assume that we have 4-bit shift left register and we want to shift the value of 1011 to the left by 2 positions. This means that the bits will be shifted by 2 positions and the value after the shift will be 1100. To demonstrate, Flores will present the SAP1 circuit with the shift left register.
So hello, I will be presenting our SAP1 circuit. So this is our SAP1 circuit. Here we have our left shifter, and this is the circuit that was shown earlier. So how this works is that the data from the accumulator will be sent to the bus already shifted by adding 0 at the end of the circuit. So for example, we have 1001. As we can see here, it has been shifted left by appending 0 at the end of the data. So how this works in the entirety of SAP1 is that we added an additional opcode in our instruction decoder, which is the SHL or the shift left, which has the opcode 0110 as it was assigned to our group. So if I trigger the 0110, the SHL command is triggered. So how it works is that here in our RAM, I already preloaded some data. 08 for the position of the data that will be shifting left, which is 09 or 1001. 60 is the command for shifting left, 6 being 0110, and 0 being the position of the command in our RAM. And E0 for the output of the data into our LED. And then F0 is for the halting of the circuit. So if I uh, simulate this circuit, our expected output is 10010 for the shifted output or 12. So if I start it, here we have our output, which is 12, which is correct as the value of the shifted 1001, which is 10010, is 12 in hex. And if we click it more times, the F0 command, which is halt, will be called and it will halt the circuit. That's it for our software simulation.